Welcome to 1007 ICT, 1807 ICT, and 7611 ICT. This is Computer Systems and Networks, Lecture 2B, Data Representation. So in the previous section, we looked at computer data, representing binary integers, converting from binary to decimal, powers in different bases, so base 2, base 8, base 16. We related that a little bit back to base 10. We looked at integer word sizes. So basically when you have so many bits, it tells you how many values you can represent. If you have 2 bits, you can have 4 values, and the range is 0 to 3. There was a table that we looked at for that. We looked at converting decimal to binary. We saw different ways to do that, and then hexadecimal and octal we talked about. So today we're going to look at, well, we've got these numbers, how do we add them together? And also how do we subtract them? Now when we subtract them, we're going to have to work with negative numbers. So we also look at how do we represent negative numbers in a machine that can really technically only store zeros and ones. How do you represent a negative value? That's going to be a challenge. So to do that, we're going to talk about something called ones complement and twos complement. And those two things are directly related to representing negative numbers. And the way we're going to approach this is we're going to show the problem that we have. We're going to try and solve it. We'll find that it's not sufficient, the first attempt that we make. The second attempt is also not sufficient, but the third attempt, when we try and solve it, we actually can solve it. So there's a stage that we go through, a series of stages. And then we look at representing character data, images, and audio. So at the end of this lecture, you will have learned how to perform binary addition, how to represent negative numbers, how to apply ones complement and twos complement, and then you'll have gained an understanding of how character data, images, and audio are represented. And you'll notice that there's a difference between these things. So the difference is, one of them is you learn how to do something, you will be able to process this, apply it. The other one is you get some basic background information on how this works. Can you see the difference in those learning outcomes? So we will be working specifically in the workshops on learning how to do this, or how to perform this, adding numbers together, subtracting numbers from each other. So in binary addition, well, how do we add up binary numbers? Well, just like normal addition, we add up each binary place and take any carry over into the next column. So I want to stop there just at this point and say, look, that's what we're going to be doing. Yep. To do that effectively in terms of looking at this part of the lecture, I'm going to do a little bit of a recap. Okay, so last time what we did was we talked about base 10. Okay, so I'm just going to lead up to this part and go through a series of steps, and it will hopefully make it a little bit clearer what we're saying here. So base 10, we said, for example, we had a number like 347. Now we said that this was 10 to the 0, this is 10 to the 1, and this is 10 to the 2, which means this is the hundreds column, this is the tens column, and this is the ones column. And really, this is 3 times 100 plus 4 times 10 plus 7 times 1 is 347 base 10. And we had a formula or an equation that we used. There was a summation symbol. Do you remember that from the other day? Okay, so I've just compressed that into a very short version here, but that's basically what we're doing. And so the things that we were looking at were 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. These are the column values, how much each column is worth. And then the number that's in this column, we just multiply by the column value, so 7 times 1 is 7. 4 times 10 is 40. 3 times 100 is 300. What's the next one, 1,000? Yep, so whatever was in that column would be multiplied by 1,000. You add them together. Okay, so that was for base 10. Then we looked at base 2. So what I mentioned yesterday was that base 2 is exactly the same, it's just the base is much smaller. We have a lot less digits to work with. So if I have a number like this, 11010 base 2, this is the 2 to the 0 column, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. Same setup. So 2 to the 0 is, well, anything to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16. It just doubles each time. Okay, so looking at these column headings, and I'll try and use a different color here, 1, 2, 4, 8, 16. So when I add these up, I add up one lot of 16 plus one lot of 8 plus no lots of 4 plus one lot of 2 plus no lots of 1. Does that make sense? Great. So if we add them up, what do we get? 16 plus 8 is 24, plus 2 is 26. So this number, 11010 in base 2 is 26. That's how we convert that number. Okay, and I think you'll see that if you practice this a bit, this will become very quick. Right? This is something that, it'll become pretty easy very quickly. So we also looked at converting decimal to binary. So if I have a decimal number and I have something like 21, the process that we used was, well, we want to find the biggest power of 2 that still fits inside 21. So we just start counting. 1 still fits, 2, 4 still fits, 8 still fits, 16, we're getting close, 32 no longer fits. Does that make sense? Okay, so 21. Is there a 16 in 21? 116. So 116, and we subtract 16 from here, and now we have how much left? 5. Yep. So is there an 8 in 5? No. Is there a 4 in 5? 1, 4. So we subtract 4 and we get 1. So is there a 2? No. Is there a 1? Yes, we subtract 1. And you'll notice I'm going through the whole process. I'm doing the full subtraction so that I end up with a 0. If I don't end up with a 0, I've made a mistake and I should start again. Make sense? It's very easy to make mistakes in this subtraction here. So one of the skills that you're going to be refreshing most likely is subtracting little numbers from each other. We may be using a calculator to do that these days, right? So I know I do generally. So this is something that you're going to have to do on paper, typically, because you will not have a calculator in the exam at the end of this. Right? So it's practice. Okay, so this number that we have here, 10101. Okay, that number, just looking at it, can I tell that that's the number 21? No. What do I need to do? I need to add a 16 plus a 4 plus a 1, and I get 21. So I can verify it, but I have to go through those steps. Okay, so I would always verify the number just to make sure it's the right number, because looking at 10101, I'm not even sure that that's 21 unless I do that calculation. Yep. Okay. So another thing I want to say here is this is working with only how many bits? 1, 2, 3, 4, 5 bits. Now typically I mentioned we work with 8 bits. So actually there is a 32 column here, there is a 64 column, and there is a 128 column typically, because there are 8 bits in total. And these columns would have zeros in them. So you should still fill them in with leading zeros. So typically if you have a question, it'll say you are working in 8 bits, or you're working in 16 bits, or however many bits this architecture has that you're working within. So typically you will be filling in all 8 bits, and that's how you do it. You just fill in leading zeros. Can you fill in with leading ones? Would that make sense? If you put ones here, would that change the answer? Yes, so you won't fill in with leading ones, you'll fill in with leading zeros. Okay, so I just want to mention that. Now, we were talking about addition, so I just went through that just to recap that part. But addition, so when we do addition, we do something like this. 3 plus 5 is 8. I'm a little concerned. 3 plus 5 is 8. Okay. 3 plus 6 is 9. 3 plus 7. 10. Now actually I say 10, but it's not really 10. Yeah, I know we say 10, but this is the ones column and this is the tens column. There is a 0 in the ones column and there's a 1 in the tens column. Do you remember that from previously where we looked at those columns? So that's actually what's going on. Now we take a shorthand and say 10, which is fine, but there's something else going on there, and that you can use for the binary numbers as well. So what about 3 plus 8? We would say 11, but actually it's 1, 1, and 1, 10. Okay? So the reason I'm doing it that way is so that we can see the similarity between this and the binary numbers. So if I have some numbers, and I'll just show you this very quickly. 0 plus 0. Well, this is pretty easy. It's 0. Remember that this is the ones column and this is the twos column. Yeah? So there's nothing in either of those columns. That's great. So let's take the next case. 0 plus 1. Also pretty easy, it's a 1. And this is the excuse me. This is the ones column, the twos column, so still okay. What about here? 1 plus 0 is still 1. Ones column, the twos column is fine. And you'll notice just what I'm doing. I'm just going through them in sequence. Yeah. And then the last one, this is the one that's going to be tricky. 1 plus 1. Now the answer is obviously 2, right? 1 plus 1 is 2. How do we write that? 0 in the ones column and a 1 in the twos column. Okay, so this is the ones column and this is the twos column, which means actually there are leading zeros here. And we're not seeing them because I didn't write them, but are they actually there? Yes. And so this is 0 plus 0, and this one has a carry of 1. Does that make sense? We would call this a carry out. It's going to the left and it's moving to the bigger column. Is this the same as a normal addition? Yes? If something's too big for this column, you just give it to the next column over and they deal with it, and so on. So it's the same principle. Now, I've shown you a carry out. In reality, if I have a number like this, okay, I can get this situation where there's a carry out and that carry out becomes the carry in for the next one. Does that make sense? If I have something and I give it to someone else, they have to receive it. Does that make sense? So potentially on this side here, there is another carry coming in from the next column. Yeah? We're not really showing that at the moment. So there are actually more cases than this. These are the basic 4 cases, right? But there are more cases. And the other cases are 0 plus 0 plus 1 coming in from the right. This would be a 1. What about 0 plus 1 plus 1? 0, 1, and there's a carry in here. Does that make sense? Yes? So again, just looking at that one, this is the ones column, this is the twos column. There's nothing there. This is the ones column, this is the twos column. Well, 0 plus 1 is 1, plus 1 is 2. That means we will have a carry here, and it will go into the next column. And in this column, we have actually 0, 0, and a 1, which is a single 1 in that column. Can you see how it's set up? So the next one, and you'll notice I'm just copying these guys here. So this one here, 1 plus 0 and a 1 coming in will be same situation, 2, right? So this is 0, there's a carry here, and there's a 1 in this column. So when I read this, if I say 1 plus 0 plus 1 is 0, carry the 1, and then in this column there are 2 zeros and a 1, and that means the answer is a 1 in this column. And the last one, again, this is the tricky one, a 1 and a 1 and a 1 coming in. Well, 1 plus 1 is 2, plus 1 is 3. 3 is, these are the columns, 3 is a 1 in the 1 column and a 1 in the 2's column. Now this may take a little bit of time to get used to, you'll do a lot of practice on this, but what I recommend that you do at the start is just write out these cases, there are 8 of them, and just look them up initially. Does that make sense? It's a really simple way to do that. So whenever you get one of these cases, and you'll see if you get a number like this, 11110011, right, you will look at this and go, okay, 1 plus 1 is, well, which case is it? This one, you get a 0. Make sense? And a 1 coming out. So 1 plus 1 plus 1 plus 1 is a 1 with a 1 coming out. And that would be this case. Now I'm doing that very quickly, but in the labs you'll get practice at this stuff, right? So please do put some energy into just starting with this because it's the basis of what we do later on. Okay, and as I said, there are only 8 cases. So once you get them down, this is going to be actually fairly straightforward. Initially it might seem a little bit challenging. So what we just looked at was binary addition. How do we add up binary numbers? I showed you the 8 cases, and this basically says, look, we add up each binary place and take any carry over into the next column. That's what we just did. Exactly the same as you do in base 10. It just looks a little bit more tricky because there's only zeros and ones. And you will do a lot of carrying. Why will you do a lot of carrying? Because the columns are very small. Every column can have a 0 or a 1, and if you have too much, you have to carry it to the next one. Right? So there will be a lot of carrying going on. So if you have multiple bit addition, let's have a look at some of these examples. Okay, so there's a bunch of examples then there. I'm just going to walk through some of these. So 2 plus 4, and the answer is 6. Okay, so 2. Now I'm going to work in 4 bits, just because it's nice and easy for me to not do all 8, but technically there would be 8 bits here, right? There'd be a lot of zeros at the start. So this is 2. How do I know that? Because this is the 1's column, the 2's columns, the 4's column, the 8 column. Okay? So what is 4 going to be? 0, 1, 0, 0, and this is 4. We happy with that? It's just a single 4. And I add them together. Well, now I need my cases. 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 0 is 0. The answer is 4 plus 2 is 6. Great, works. Yes? Okay, it's a great question. So the question is, what happens in the computer? You only have 8 bits. The last bit, the 8th bit, can have a carry out. Something falls off the end. In that case, the machine will recognize that something fell off the end, but it won't store it. You only have 8 bits to play with, so your program could recognize that. That's a particular situation, say, oh, something fell off the end, maybe that's an error, I have to do something about that, or maybe it's expected, and there's a process that I go through. So yes, it is possible, and the program around it can deal with that. So the system recognizes that as a thing. Yeah, so good question. And we'll see that this one did not have any carries, correct? So I set up a really simple one to start with. Let's do one that maybe has a carry. So the next one will be, in that example, 7 plus 12. So 7 plus 12 is 19. Okay, so let's do 7. This is 7. And it's 7 because this is the 1's column, the 2's column, the 4's column, the 8's column. 4 plus 2 plus 1 is 7. So 7, this is 7, plus 12. 8 plus 4 is 12. Is that correct? Okay, so now we do the addition. So 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is, it's a 2, and a 2 is a 0, carry the 1. Right? You notice where I'm putting that 1 in a nice, easy to see place, because it's going to get very confusing if I do these carries. Okay, so find a way to represent that nicely for yourself. So 1 plus 1 is 0, carry the 1. That means in the next column I have a 0 plus a 1 plus a 1. So that's a 0, carry the 1. Now, this is that situation that was mentioned before. I only have 4 bits. It's fallen off the end. Well, in a normal computer, I will have more bits. I'll have 8, actually. Right? So the next column would be the 16's column. There are 2 zeros in there at the moment. 0 plus 1 is 1. Now just have a look at this, right? If I have this situation. In the situation where the computer only has 4 bits, what's my answer? 0011, which is 3. So the answer inside the machine, if I only have 4 bits, will be 3. Is that wrong? Yes and no. Okay, yes, the answer that I expect is going to be 19, so yes, it's wrong in that sense. But in terms of the computer, actually, if I just added a 16 on the front, so this part of the answer is correct. It's just not complete. Yeah? 16, that's this column, plus 3 is 19. Does that make sense? That's why I say it's partially correct. It's just not the complete answer. Okay, it doesn't mean that this part is somehow wrong. It is correct, just not complete. Okay, so in this particular case, and on paper, you can always add more columns. You can just add one to the left. Now typically, a question that you get will say you're working in 8 bits, which means you cannot add more bits than 8. Inside a computer, can I just glue another bit to the chip? No, it's limited, it's fixed, so you're going to have to work within those constraints. Yeah, but on a piece of paper, if it doesn't say how many bits you're working with, you're free to add as many. You could have 25 bits. It doesn't actually make much difference. Yep. Okay, last one here will be one 3 I think plus 7 was the last one that we looked at. So 3, this is 3, 1, 2, 4, 8. That's 3 plus 7. So 3 plus 7, so 4 plus 2 plus 1 is 7. 1 plus 1 is 0, carry the 1. Now this is why this example is here. 1 plus 1 plus 1 is 1, carry the 1. 0 plus 1 plus 1 is 0, carry the 1. 0 plus 0 plus 1 is 1. And the answer is 10. An 8 plus a 2. So, again, if you're looking at this, if you have two 1s, the answer is a 2, and that if there's a 2 in the answer, it'll be a 0, carry the 1. If the answer is there are 3 1s, in this case, it'll be a 1, carry the 1. So you can find simple ways to remember that for yourself also. Okay, so that was just looking at some examples, and please do try these examples out yourself, see how they go, right, and get a little bit of practice with them. There's another one, 9 plus 6 over there as well, which we didn't go through. So those were just basic, simple, positive number additions. So it's not too bad, right? We all know how to do the additions in base 10. It's exactly the same mechanism, just looks a little bit more tricky because there's only zeros and ones. The thing that we have a problem with is negative integers. If we want to do subtraction, the computer cannot represent negative values directly. It's got a 0 or a 1. There is no place in there for a negative 1. That gives us some problems. Alright, so we can't easily directly represent a negative 1 with our bits. We can only represent positive values. So somehow we have to take a positive value and make it a negative some way. Right, that's what we're going to achieve in the next part. So one way to do that is to say, well, look, we'll just take one of these bits, and we're going to take the left one, the furthest one on the left. Normally, that is the 128 column, if we have 8 bits. And we're going to take that bit, and if it's a 0, it's going to be a positive number. If it's a 1, it's going to be a negative number. How many bits do we have left? We had 8. We've taken 1 away. We now have 7 bits left. If you're looking at what happens every time you add a bit, you double the number of values you can represent. If you take 1 away, you halve the number of values. But they can be positive and negative. You don't get less values in that sense, you just get the range changes. Does that make sense also? So now you have not just 0 to 255, but you have negative 127 or 128 all the way up to 127. Yeah? Okay. So there's an example there, and I'll show you the example, or a version of it. Here, and I'm going to work in 8 bits now, and it's important that I use all the bits because it's the first bit on the left that's important. So I need all of them to see how that works. So we'll do 1, 2, 4, 8, 16, 32, 64. This would be the 128 bit, correct? We cross that one out and we make this the plus or the minus sign. So 0 in that column is a plus, 1 is, a minus. So let's start with the number 2. So 2 is positive, we agree with that? And 2 is, and just do a very simple one, 2 is this. Yeah, it's a really simple example, just so it's really clear which is which. So what's negative 2? Well, negative 2 will be negative, there's a 1 there, and it'll be this. Really simple. Do you think it works? No, it won't work. Right? We can't get this to do our subtraction or our negative numbers properly. It's a good start, but we'll show you just in a second that there's a problem with this. There's actually a couple of issues that we'll run into. Remember at the start I said we're going to go through a series of things. We're going to show you one that sort of, it's an attempt, it doesn't quite work. The next one doesn't quite work, and then finally we put it all together and we get one that works. Okay, so just keep that in mind. This one on its own does not solve the problem. And one of the reasons it doesn't solve the problem is have a look at this number. What number is this? What number is this? Negative 0. We have positive 0 and negative 0. Are they two different cases? Well, not in the real world, but in this example, are they two different cases? Yes. And so what we have now is we have a number line that goes like this. Minus 1, minus 0, 0, and then 1. Do you think that there will be some problems with our numbers when we have an extra space on the number line? Yes, we're going to run into some issues. So that's what I'm saying. This is a good solution initially, but when you actually try and implement it, there's a problem. We have to overcome this problem. So just keep this in mind. The problem is that we have an extra space on the number line. So a simple solution, just mentally, right, would be that we can jump over that space. We could either add 1 or subtract 1 potentially. Does that make sense? If we shift everything to the right, yes, so because there's this extra gap, if we can move this guy to here, then this one will become here and this one will become here. Potentially we can overcome that gap. Just visually try and think about that. Okay. Alright, so what we just said there was that we have potentially some issues, but it's a good start. We definitely want to be able to represent that it's positive or negative. We have done that, right? We can label it saying it's positive or negative. That's the first step. Okay, and then basically just showing what I just went through in that example. Right, so this couple of little diagrams here. So we talked about the problem. We have plus and minus 0. Okay, that is a problem. We saw why it's going to be a problem. And what we can do is view subtraction in terms of addition. So B minus C would be the same thing as B plus minus C. Would you agree with that? Let me just write that up. So, and I say B, let me just write this here. So if I have B minus C is the same thing as B plus minus C. Give me an example. 3 minus 5 is the same thing as 3 plus minus 5. Is that true? Yeah, so maybe just putting numbers in it makes it a bit more easy to see. But yes, this is absolutely true. So what we're going to try to do is we're not going to try to implement subtraction actually directly. We are going to use addition, and we are going to change the second value. We're going to take that second value. If it's positive, we're going to make it negative. If it's negative, we're going to make it positive. Is that kind of a cheat? It's a working around it. We're not actually going to directly implement subtraction. Now, one of the things that you want to be aware of, I guess, with computing, if we can reuse something, we can save space. We have space limitations on our chips, on our components. What do you think? Yes. We're trying to miniaturize everything, so if we can reuse stuff, we will. So if we have an addition unit, and we can take that addition unit and change it a little bit so that it can also do subtraction, we will most likely do that because it makes sense to do that. Okay, so we're not actually going to directly implement subtraction, at least not in this course, right? So we're going to use addition and turn this guy C into a negative. Okay, so what I'm talking about here is, again, I'm just going to use a number line, right? So minus 3, minus 2, minus 1, 0. I'm not going to put in the extra 0, 1, 2, 3. So this is a normal number line, right? Now what I'd like is it should look something like this with the different pieces. Yeah? I would like to have, if I have 3 minus 3, which is the same thing as 3 plus minus 3, yeah? I would like to have this happen. So this is 3. This is minus 3 on my number line. And when I add these together, what will happen? They will cancel out and they'll end up here on the 0. Is that correct? Because they cancel each other out. So one of them is going one way, the other one's going the other way. In our environment that we have here, we have a problem with that. All our numbers are going this way because they're all positive numbers at the moment. Does that make sense? Now we're putting a label on it saying it's plus and minus, so we'll see how that actually works, but we need to overcome that part. You actually need to have a negative quantity. So let's look at an example. So down here it says plus 7 minus 5. That's the example on this slide. I'm going to go through that one and just show you what's going on there. So plus 7 minus 5. 7 minus 5, and the answer to that is, should be 2. Yes? That's what we expect. So let's do the subtraction. So we got 7. So this is 7. Yep. Remember, I'm taking out that plus and minus part. The 128. So this is 7. I'm happy with that. Now, how do I work out what minus 5 is? Well, what we said was, look, let's start with this is 5. We agree with that? So what's minus 5? Minus 5 is... This is minus 5. Okay? Just put a minus sign on the front. Great. So now let's get rid of that so it's not confusing. So let's take 7 plus minus 5. We add them together, slightly bigger, and let's do that. 1 plus 1 is 0, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1, 0, 0, 0, 1. What number is this? Well, it's minus. Oops. Why is it minus? Because of this. So that's wrong. Okay. Maybe the rest is fine. We'll see. What's this? This is an 8, 4, 2, 1. So 8 plus a 4 is 12. Minus 12. Okay, there's a 2 in there. That's pretty good. Right? The answer is supposed to be 2, but it's way off. Now, what have we actually done? We've taken 7 plus 5, which is 12, and then we just glued a negative sign on the front of it. So what are we doing? We're adding positive values. Remember our number line? We're only adding in the positive part. We're getting a bigger number rather than a smaller one. And we've just glued a negative sign on the front. So is this really working? No, it's not working. It has some problems. Okay, so the first thing we need to do is, okay, this is not actually going to work as a minus 5. It's still a positive 5 somehow. Okay, so we need to address that part. So the next thing that we do is we try and address that part. So we have this idea called 1's complement. Now a complement is just the opposite. Right, so if I have a number, like it has a 0 in it, the complement will have a 1 in that place. If I have a 1, it'll be a 0. So it's just the opposite. It's a very simple process. The machine can do this very quickly actually as well. It's very efficient. So we can flip a bit. So we start with a 0, we can flip it to a 1. We start with a 1, we flip it to a 0. Okay, so we can complement or flip a binary number by complementing or flipping each of its bits. Change all the 1s to 0s or all the 0s to 1s. So there's an example down there. I'll just show you an example here. And it doesn't really matter what number we're working with. So let's say I've got this number 0001, 0010. I don't really care what that value is. It doesn't matter. Right? What's its complement? The complement will be all the 0s replaced with 1s and all the 1s replaced with 0s. So this will be a 1, 1, 1, 0, 1, 1, 0, 1. We okay with that? Yeah? So I don't know what this number is. And like I said, it doesn't matter. I can work it out pretty. It's 2 plus 16, which is 18. Yeah? Okay. But it doesn't actually make any difference what the value is. Now, I flipped those bits, and you notice I worked from the left to the right. In this case, that's fine. It doesn't matter because there's no carry, there's no implications. Usually we have to choose a side to work from, either the right or the left. Does that make sense too? So with this one, it doesn't actually matter because it's just in place. So here's something I want to show you. If this is really the opposite, that's what we're claiming, that this is the opposite. So what we did was we flipped all the bits. If this is the opposite, when I add them together, what should I get? A number like 3 and its opposite minus 3 should give you 0. That's what I expect, hopefully. So let's do that. 0 plus 1 is 1. Okay, that's not great. 1 plus 0 is 1. 0 plus 1 is 1. 1. 1. All the values will be 1. Okay, so that doesn't sound like a 0 to me, but it's actually very close to 0. I'll show you something. So if I add the number 1, this is the number 1. Would you agree with that? If I just add 1, 1 plus 1 is 0, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. This is going to go all the way through. And this one is going to fall off the end, which is what you were saying before, right? We don't count that one, we don't keep it. What's the answer now? 0. Do you remember this setup? Remember we had this extra space? If we add 1, right, plus 1, we can jump over that space. Can you see that? Okay, so we introduced a problem and this is going to be a solution to it. So keep that in mind. So the solution is actually Let me show you. So the next thing is, we talked about one's complement. I showed you an example. I showed you that for this one, the one's complement, you can try this out on this particular slide. Just using one's complement is not sufficient still, right? We were able to flip all the bits, but we didn't get 0, we got all ones. Now, if we get all ones and we just add 1 to that, it will flip around to be 0. Does that make sense too? So you can try that out for yourself. If you take a number, a binary number, flip all the bits, add the two numbers together, you'll get all ones. If you add 1 to that value, it will flip all those bits to zeros. Yep, you can try that. And so what this is saying is, when we do this one's complement process, we're still not quite right. It's still wrong. It's very close though. We're only ever out by one value, just one, a single one. So the solution is, have a plus or minus bit. Great. We need one of those to represent whether it's positive or negative. Complement the number and then add 1. It's a little bit involved, but that's the process, and that will get you the right result. That is called 2's complement. So we had just add the plus and minus bit. That was the first part of it. Then we said 1's complement, which is just flip the bits, okay? And then we have 2's complement. So this is the final stage. This is the thing that actually works. And 2's complement is have a plus or minus sign, flip the bits, add 1. And that will work. So there's a bunch of different examples here. Again, I invite you to work through this. You will work through some of this stuff in the labs as well, so you'll get plenty of practice at these things. So let's do an example just to show how this all works. So let's do this one, 46 plus minus 46. And you would expect to get 0, right? Okay. So 46. We have 32, an 8, a 4, a 2, and nothing. So let's work that out, make sure that's correct. So 42. 32 plus 8 is 40. Plus, sorry, 44, 46. That's right, so I'm working on 42. 46. Is this 46? 32 plus 8 is 40, plus 4 is 44, plus 2 is 46. Okay, so we're happy with the 46. Let's do the 2's complement, right? So that's 46. So what's minus 46? It's the flipping of it, right? 1, 1, 0, 1, 0, 0, 0, 1. So this is the flip part. Is this minus 46? Not quite. What do we still need to do? Add 1, right? So we add 1, and we do this addition, and what do we get? 1 plus 1 is? 0, carry the 1, or 1. 0, 0, 1, 0, 1, 1. So this apparently is minus 46. Now if we add those two things together, yeah, what do we get? We should get 0. So let's take this number, 0, 0, 1, 0, 1, 1, 1, 0. 0, 0, carry the 1. 0, carry the 1, 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 0, carry the 1. Can you see how that works? And I did that very quickly, but you can certainly review that. Basically, this 1 will travel all the way to the end and leave zeros behind it, and this one will be discarded. It doesn't fit anywhere. So what's the answer? 0. So I took a number, 46, any old number you can try. I got its negative value, minus 46. How did I generate that? Well, I took 46, I flipped the bits, I added 1, and then I had the negative version of 46. In this case, it's this number here. If I add them together, they cancel each other out, and we just verify that that works. So this will probably take a little bit of practice on your side to just go through this, verify it. Now, what I do want to show you is, okay, this is a lot of work. There's a lot of steps involved. I need for you to do this initially this way so that you get facility with the process, that you try it out. But there is a quicker way. And the quicker way is we call 2's complement approach 2. It's much, much quicker and simpler, but you need to understand how it works. So please do try it out the long way first. It'll do two things for you. It means you'll understand what 2's complement. It also means that you'll get better at addition and subtraction, right? So just in general, that's a good thing. So 2's complement approach 2, it's a simpler method. The approach is like this. Start from the right-hand side of the number. For all the bits to the left of the first one, change everything that's a 1 to a 0 and all the zeros to 1s, and that's basically it. So let me show you what that looks like. So if I have a number like this, let's just pick a nice 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0. Something like this. So what it says is find the rightmost one. So the rightmost one is here. Yes? Is that the rightmost one? Keep the rightmost one and everything to the right. This one is flip. Okay, so if I do that, I keep the 1 and the 0 here, and then I flip this. This is the answer. Is that much simpler? Much quicker, right? It seems... I'm not sure why that works. Just looking at it, I know why it works, but I'm not sure, just looking at it from that explanation, why does this work? So what you need to do is convince yourself that this actually works. Try out some examples. Try the long way. Try the short way. Should get you the same result. Now here's another thing that you can do. I've gone one way with this. You can reverse this. So if I take this number, and apparently this is what kind of number? There's a 1 at the start. This is a negative number. The start one was a positive one, so yes, I think it's negative. If I do this again, what should happen? If I change 3 to minus 3, and I change it again, what should it be now? 3, the same number, right? Yeah. So let's do it again. Keep this, find the rightmost one, keep it, 1, 0, and then flip these bits. Is it the same number as at the start? Yes. Okay, and you can verify that it's going to work, right? So please do that for your own sake, and just do some examples. Do some long versions, try it out, and then just compare it with this one. I'm happy for you to use the short version. It's much quicker, but I would like for you to understand why it works, right? Or basically the process for how it works, because it's a little bit arbitrary if you don't understand the mechanism behind it. Okay, so that's the short version and the long version. Next thing we look at is just number representations. I'm not going to go into this in a lot of detail, but there are different ways to store numbers. They take up different amounts of bits. You can store integers with a plus or a minus sign. That's the signed version, or you can store the unsigned version. Doesn't have a plus or minus sign. Unsigned versions have more values to play with because you don't waste a bit for the plus or minus sign. And there's characters. There's lots of different types of values you can work with. The computer has lots of different inputs and outputs. You need to be able to work with all those different types of inputs and outputs, like keyboard presses, text displays, bitmap images, graphics, audio, video, and each of these types will have its own internal data representation. They're all different. Okay, and in your program, when you write the program, you'll say this is an integer, or this is a float, or this is a double, or whatever the type is. Okay, so at some level the machine understands what the restrictions are on this particular data. One thing we use a lot is character data. So we're going to do this fairly quickly, but basically there's a table, the ASCII table, which tells you if you have this number, like 65 in decimal, it maps to a character. 65 in decimal maps to the character capital A. 66 maps to the character capital B. 67 capital C, 68 capital D, and so on. 97 little a, 98 little b. Seems like random kind of numbers. Why would you start at 97 for the first one in the series? There's reasons behind that. It's actually very clever how they've done those things. There are numbers. So decimal 48 is 0, decimal 49 is 1, decimal 50 is 2, and so on. There's in the blue, there's this hexadecimal word 1007 GC. Those are the characters. So the 1 you would look up in the table, and we're using hexadecimal. The table at the bottom for 1, 49 in decimal, 31 or 31 in hexadecimal. So you'll see 1 relates to 3-1 on the right of that equal sign. 0 is 3-0. There are two zeros, 1-0-0, so 3-1, 3-0, 3-0. 7 is 3-7. G is a capital G. You'd need to look up in the letter part of the table, and it's 4-7 in hexadecimal. So you can convert any letter or any symbol that you want to some number somehow, and there are different encodings for that. Here's an ASCII table. This is an odd table in the sense that this ASCII table, what we're doing is we're going across the top first, and then we're going down. Normally you go down first and across. This one is the opposite, just the way it's been represented. And you'll see there, the capital A, it's 0x41. You're going to use this table in your workshop, so you'll get familiar with it. But basically 41, that means you go across 4. You see column 4 up the top. Here it is, column 4. And 1 is, this is the 0, capital A. Yep. So if I would ask you, what's 5, 5? Well, you go across 5 first, and then you go down to 5, and you'll get the capital U. So this is basically a lookup. Okay. And you will use that table for different purposes, right? So there's a mapping between letters and numbers, actually. So there are other standards for representing characters. We just talked about ASCII. There's EDCDIC, which is quite a mouthful, right? And there's Unicode, and probably you're familiar with Unicode if you're doing any kind of web development. There are different flavors of those, UTF-8 and so on. And you need those so that computers can work out what encoding, what character set to use. For example, if you need Japanese characters, right? You're going to have a way to represent those characters, and when you see a particular number, it should map to the correct Japanese character. Same thing with English characters, Chinese characters. Doesn't matter which language, there will be a mapping between those. Some languages are bigger than others in terms of the characters and the symbols they have, so you might need quite a little bit of space, for example, for Chinese characters. There are a lot of those characters. English, how many characters do we have? 26, upper lowercase, so that's actually quite a small number. Okay, so you don't need that much space for those. But every environment will be slightly different. Bitmap images. So one of the things I'll show you here, we'll just talk about this. It's basically just an array of pixels. So if we have, let me just get this guy. Let's say this. If we have some pixels. So basically imagine that this is a pixel on the screen, and each pixel is 1 bit. The bit can be on or off. It's a black and white screen. So if you look in here, in this picture here, you'll see that there is the shape of a spaceship right here. Right? All the zeros are black, all the ones are white. Now you can add more colors, in this case shades of gray, by just adding more bits. So instead of 1 pixel being 1 bit, if you make it 4 bits, you can have 16 different colors or shades. So each of these boxes here in memory now goes from 0 to F, or 0 to 15. And you'll still see that here is the shape for the spaceship. But it's now made up of different shades of gray or different color values. Does that kind of make sense? So you can map screens to pieces of data inside the computer, and depending on what data is in there, you get different colors or different shades of gray and so on. Okay, so that's another type of data that we're going to be working with, or that the computer will work with, so it needs to be able to represent those things. Color formats. Not going to go through all of them. There's just a bunch of different ways to represent colors. The main one that we tend to use is RGB, right, red, green, and blue, and you combine those 3 colors together and you can generate any kind of color that you need. Everything on is white, everything off is black. Just the red component on is red. Right? Just the green component on is green, and then there's mixing of green and red and so on. So you can get different kinds of colors. There's also other color formats that you might use. There are bitmaps, which are basically single bits to represent on and off. There are grayscale, so you only have shades of gray. Color mapped, you don't have all the colors, just some representative colors. And this is like that color palette that you see inside, Paint, for example. It's just got some of the colors. And then you have the detailed one where you can choose whichever color you want, right? And then true color, 24 bits per pixel. 24 bits per pixel is 8 for red, 8 for green, 8 for blue, for example. And then you might have another channel or another 8 bits for transparency. So whether you can look through this color or not. Audio and sounds. So audio and sounds are interesting. basically, let me just draw this. Actually, I don't want. Maybe I won't draw it that way. If you look here, there's a thing on the bottom which basically shows you just a diagram of audio signals. I'll just draw this. I think it's probably easier just to see it. So if I draw this audio signal, here is an audio signal. It's a continuous signal. Now I can zoom in on any part of this and I'll get more and more detail because it's an analog signal. In the computer, do we have infinite space? We've got limited space. So what we can do is we can sample, take particular measurements at different times and get a value. So that's this one, and this one. So imagine that this is a really nice sound or a song or something. If I only sample here, is my song going to be very nice? Does it look a lot like the shape, the original shape? No. So it's going to be very right, that kind of sound. So the more sample points I have, the better the reproduction of this sound is going to be. Can I ever reproduce it exactly? No, I don't have enough space in the computer to do that. The other thing is that our ears are not that great. There's a point of where there's no point making more data, taking more samples, because we literally can't hear more than this level of detail. Yes? That's possible. I'm not familiar with that. So the comment was that maybe there are ways to take a sample and you can always reproduce that. I'm not familiar with that particular thing, but it's certainly possible. Yeah. But the basic idea is that just sampling more and more is not necessarily going to get you the outcome that you want, which is better sound quality, because we probably can't hear past a certain point. Right. Now the reason I say that is because if you sample more, you need more space. That means your file size gets bigger, and at some point it's not worth the space to do that. Okay, so that was audio. And in summary for this section, so we went through quite a bit of stuff. We looked at binary number operations. We looked particularly at addition and subtraction. Those are the two key things, and I would like you to practice those, and you will get familiarity or facility with those during your next workshops. The next thing that we do is digital logic. So how do we take these signals and how do we basically process them so that we can make decisions? And that's the end of this section.